Thank you for introduction. I am Yamasaki, working as an assistant professor in the University of Tokyo. This talk is about a fundamental question of characterizing entanglement cost in quantum information theory. But this talk is about, we talk about this characterization for infinite dimensional physical systems. As you will see in the talk, this is relevant for us living in a physical world that is inherently infinite dimensional. This work is based on a joint work with Kotai Kuroiwa, Patrick Hayden, and Lov Golami. Quantum entanglement is a unique feature of quantum state. A quantum state is said to be separable if it is a convex mixture of product states, and is said to be entangled otherwise. Entanglement is known to be serve as a resource to assist local operations and classical communication, or LOCC for short. It is useful for various quantum information processing tasks, such as quantum teleportation, superdense coding, and device-independent quantum key distribution, for example. However, we may need a very particular form of entangled state to achieve these tasks. For example, this task requires E-bits, that is a maximal entangled state of qubits. In general, quantum state is given by a mixed state, and important task in entanglement theory is entanglement distillation, which converts given many copies of mixed state raw into E-bits. The reverse task is called entanglement dilution, and it's also important in entanglement theory. One of the central questions in entanglement theory is to clarify optimal protocols and fundamental limits in manipulating entanglement. The optimal performances of in entanglement distillation and entanglement dilutions are fundamental in the theory of entanglement. In the entanglement distillation, distillable entanglement is defined as a maximal number of E-bits that can be obtained per copy of raw. And in the same way, in the entanglement dilution, entanglement cost is given by the minimal number of E-bits required per preparing copy of raw within asymptotically vanishing error. While these are opposite of each other, it is indeed very hard to characterize distillable entanglement. And in particular, it is even unknown whether this distillable entanglement, how to decide whether this is distillable entanglement 0 or not. In particular, if a given state rho is a positive partial transpose state, then we know that this distillable entanglement is 0. But if it's non-positive partial transpose, we don't know whether this is, it has been a very long-standing open problem, whether this is necessarily sufficient or whether there is a quantum state that is non-positive partial transpose, but still this is 0. By contrast, one of the pillars in entanglement theory is the exact characterization of entanglement cost, given by axiomatically defined entanglement measures called regularized regularized entanglement formation, as I will explain in the next slide. Entanglement measure is a family of functions of states monotonically non-increasing under LOCC. Examples of entanglement measure include distillable entanglement, entanglement cost, and entanglement formation, as I will introduce here. For pure states, entanglement entropy is known as the entanglement measure. Entanglement entropy is given by the quantum entropy of a reduced state of a bipartite pure state. But this is not directly applicable as this is not directly used as an entanglement measure for mixed state. One way of generalizing this construction to entanglement measure of mixed state is an entanglement formation. For this generalization, we represent mixed state as a finite ensemble of pure states and consider the average of entanglement entropy. This construction gives the entanglement formation as an entanglement measure for mixed state. Entanglement formation is not known to be additive. So it is known that this is not additive. So the regularization of entanglement formation provides a different entanglement measure. The previous results, the known results of infinite dimension shown by Hayden, Hordesky, and Tarhal shows that entanglement cost can be characterized by the regularized entanglement of formation. This provides an important operational entanglement measure. This represents important operational measure in terms of axiomatically defined entanglement measure. However, the physics inner nature is not as simple as theorists just simplifies for the analysis. For example, if you go to the lab of superconducting qubit, then we make qubit using the ground state as 0 and the first excited state as 1. But at the same time, we have infinitely many energy levels just above the qubit. Our current technology may not be advanced enough to fully control all these energy levels precisely. But in principle, the law of physics does not prohibit the use of all these energy levels. Also in the entanglement dilution, the state to be actually prepared by the protocol may live in the infinite dimensional physical systems in principle, which is represented by the separable Hilbert space with countably infinite energy levels. The problem here is that even if the target state rho to be prepared is finite dimensional, in principle, no proof rules out a possibility of using infinite dimensional local operations for approximating these copies of rho, so as to go beyond the optimal finite dimensional protocol. To address this problem, existing works may provide some bounds on entanglement cost. By contrast, in our work, we fully characterize the entanglement cost for infinite dimensional physical systems. In our results, for any finite or countably infinite dimensional state rho satisfying the condition that at least one of the local quantum entropy should be finite, meaning that implying that entanglement of formation of the rho should be finite. And under any LOCC that may use infinite dimensional systems, the entanglement cost is characterized by the regularized entanglement of formation. In this way, we show the same formula as before, even though LOCC may manipulate infinite dimensional systems. We also show that this formula also holds even under infinite dimensional separable operations. That is a superset of LOCC. To obtain this result, we need to develop a new proof techniques for infinite dimension, since the finite dimensional proof no longer works in our setting. In this way, our result established a fully general characterization of entanglement cost, applicable regardless of the system is finite or infinite dimensional. To describe our result in more detail, I will introduce the infinite dimensional definition of LOCC and separable operations. Operations implementable with finite round of classical communication is known to be finite round LOCC. This is in principle what we can do in labs with finite resource of communication. Conventionally, LOCC is defined in the limit of infinite round classical communication. What LOCC can approximate is represented as the closure of the set of LOCC. And this is known to be strictly larger than the set of LOCC, even in the finite dimensional case. Here we take this closure in terms of a conventional choice of topology in dealing with infinite dimensional operations called topology of strong convergence. The set of separable operations is a superset of LOCC. Corresponding to the finite round LOCC, we introduce the countably separable operations. That is, operations represented as by a class with some class decomposition with product class operators. The set of separable operations is defined as a closure of countably separable state so that these separable operations can prepare any separable state that may only have a continuous decomposition rather than discrete decomposition. Our contribution here is to clarify consistent definitions of infinite dimensional operations to extend finite dimensional LCC and separable operations to infinite dimension, and to recover the non-inclusion relations between operations in the finite dimensional case. With these classes of operations, we define entanglement cost in infinite dimensional case as minimal number of EBITs required per copy of row under the class operations used for implementing a protocol. As a resource, we use finite dimensional EBITs that is embedded in the infinite dimensional systems within a finitely supported subspace. The state to be prepared actually by the protocol may be infinite dimensional, even if the target state row is finite dimensional. As for the entanglement of formation, we define it as the average of entanglement entropy optimized over countably infinite ensembles rather than finite ensemble. With these definitions, we use natural generalizations of finite dimensional entanglement measures to infinite dimensions. With these definitions, our state in infinite dimensions shows that the entanglement cost is characterized by regularized entanglement of formations under all the operations between one-way LCC and separable operations. Our analysis is divided into two parts, that is direct part and converse part. The direct part shows the achievability by constructing a one-way LCC protocol achieving this task. The converse part shows the optimality of this protocol among any infinite dimensional LCC, any infinite dimensional separable operations. The challenges here is that essential techniques in the existing finite dimensional proof do not work in infinite dimensional case, such as conversion between finite dimensional pure state entangled states, strong typicality, asymptotic continuity, and monotonicity of entanglement of formation under finite dimensional separable operations. I will explain these challenges in the following slides in more detail. To begin, I would like to explain the protocol achieving this task for pure states. In our case, we initially have finite dimensional EBITs, but the state to be prepared, the target state, is infinite dimensional. It is impossible to exactly prepare infinite dimensional state from finite dimensional EBITs, finite number of EBITs. However, we use weak typicality for applicable to countably infinite state to approximate the infinite dimensional state by finite dimensional state that is actually prepared by the protocol. A weakly typical set is a finite set of indices that appears with probability close to the power of entropy. Using this weak typicality, we construct a one-way LCC protocol for achieving entanglement entropy per copy of infinite dimensional psi pure state. The next step is to describe the protocol achieving this task for mixed states. The essential question here is, for mixed state, how we can achieve the entanglement of formation. That is the average of entanglement entropy. To achieve this in the finite dimensional case, the essential technique was strong typicality. Strong typicality says that for a very large n copies of an ensemble mixed state includes each pure state in the ensemble. Many copies of row includes some probability times n copies of each state in the ensemble. By using this strong typicality, we can by preparing each pure state in each pure state in this ensemble, we can show that the mixed state row can be prepared only at the cost of average at the cost of average over average of entanglement entropy. And this is indeed much more efficient than just preparing a very large single entangled state and then tracing out unnecessary auxiliary system. But the problem here is that strong typicality is only applicable to finite ensemble. In our case, we have infinite dimensional system, infinite dimensional state, and we need we use countably infinite ensemble to represent the state. To avoid this problem, our protocol uses the efficient protocol based on strong typicality only for a dominant finite part, and then use the wasteful protocol for negligibly rare tail part. In particular, we apply strong typicality to a dominant finite part of the ensemble. And then for the negligibly rare but infinite part, we just prepare the purification of this state and then trace out unnecessary auxiliary system. This is a bit more wasteful, but this only appears within a very rare probability. With also showing convexity and additivity of entanglement cost, we obtain our one-way LOCC protocol for mixed state, achieving regularized entanglement of formation. As for the optimality of this protocol, the existing converse proof in finite dimension connects required number of E bits for entanglement dilution with entanglement of formation using two techniques, that is monotonicity and asymptotic continuity. Both of these techniques do not straightforwardly apply to the infinite dimensional case, but I first explain this asymptotic continuity. Asymptotic continuity in finite dimensional case says that for any d-dimensional states that is at distance delta, in terms of trace distance, the difference between entanglement formation of rho and that of rho tilde scales as square root of delta times the log of the local dimension d. However, this bound trivializes if local dimension diverges, so it's not applicable in principle to the infinite dimensional case. There may also exist a similar bound applicable to infinite dimensional case if we impose energy constraint on both rho and rho tilde. But the important point is that we cannot impose any constraint on rho tilde to be actually prepared by the protocol in our case, because we do not want to impose any physics do not impose anything on the actual state to be prepared. To avoid this problem, we here use a recently developed one-sided continuity applicable in infinite dimension. This one-sided continuity says that if entropy of local reduced state of rho is finite, then for any choice of infinite dimensional state without any constraint, the entanglement formation of rho minus that of rho tilde should be upper bounded in terms of delta and some constant E. So if we reverse these roles, this upper bound does not hold. An important point is that this is applicable without energy constraint on rho tilde, as we desire in our setting. In this way, we avoid imposing dimension or energy constraints in our infinite dimensional state to be actually prepared by the protocol. As for the monotonicity, existing results show the monotonicity of entanglement of formation under finite dimensional separable operations. In particular, previous work shows that characterizes a necessary and sufficient condition on the conversion from pure state into a finite ensemble in terms of some majorization condition. And from this majorization condition, we can obtain monotonicity of entanglement formation in the finite dimensional case. Our results generalize this result to infinite dimensional cases. In particular, we use some infinite dimensional version of some linear algebraic theorem used in the existing proof to show a necessary and sufficient condition for conversion of pure state into countably infinite ensemble in terms of the same majorization condition. And from this majorization condition, we obtain the monotonicity of entanglement formation. But our analysis is indeed applicable works only under countably separable operations. And it is still left as an open problem whether entanglement formation has monotonicity under general separable operations. Nevertheless, we also show that entanglement cost under countably separable operations and that of under general separable operations are the same. In this way, our converse proof applies to general separable operations. In this way, we generalize finite dimensional converse proof into infinite dimensional cases by replacing monotonicity of entanglement formation under finite dimensional separable operations with countably separable operations, and replacing asymptotic continuity with one-sided continuity. So in conclusion, many techniques in quantum information theory indeed rely on finite dimensionality, but physical systems in nature may inherently have infinite energy levels just above the qubit. Nevertheless, with our result, a fundamental open problem of characterizing the entanglement cost has now been solved in a fully general physically relevant setting of manipulating infinite dimensional physical systems. So it may still be largely unknown whether other finite dimensional results generalize like ours, but an exciting time has come to rethink what we can do within all these infinite dimensional physical systems. Thank you for your attention.
Thank you very much. The floor is open for questions. Please approach the mic if you have any question. If there's no questions, then what do you have in mind for applying these new techniques? What other entropic quantities could you?
So the protocol here, the essential part of the protocol here is that we truncate at some point and then to generate an infinite dimensional state. So for example, for the state of light, so this is inherently infinite dimensional. So there may be some application for preparing highly non-Gaussian states, in my opinion.
Hi, can you show me the slide of one-sided continuity?
Yes.
So is this E here the energy, or?
This is, yes, yeah, this basically represents energy, yeah.
But then why do you say applicable without energy constraint?
The original statement by Shirokov basically provides some appropriate choice for some appropriate choice of Hamiltonian, this kind of energy constraint holds. So this kind of energy bound based on energy holds, and we basically rephrase this in terms of we choose Hamiltonian so that we rephrase it in terms of our condition.
So it's the energy of rho, right? Not our rho.
Yeah.
Or maybe just a quick comment. So like it turns out that if you have a state with finite energy, you can always find a Hamiltonian that satisfies the Gibbs hypothesis with respect to which that state has finite energy. Sorry, if a state has finite entropy, then you can choose a Hamiltonian that's why, I mean, there's an implicit choice of Hamiltonian there.
Okay.
Yeah, from this choice, from this condition, we can construct Hamiltonian. Yeah, that satisfies, that provides the C. Yeah.
Hi, thanks for the talk. So, what I felt like you said that even if you have qubits, they are also some kind of like infinite dimensional systems, like they're like subsets of infinite dimensional systems. So, how do you, where's the scale? Feels like there's a sliding scale of like going from some of the things you can consider with consider to be finite dimensional and get away with it, and then there's some things which you have to consider to be infinite dimensional. For example, coherent states or Gaussian states. So where is this limit where you can say that your theory is going to be superior?
So for achievability, there's no problem. If the states to be prepared is finite dimensional, we can just use finite dimensional protocol. But the converse proof is basically the problem. So if we, for example, if we allow some existing proof really needs to impose that at some point of energy scale, we need a exactly zero population on each energy level. Otherwise, yeah, the existing proof does not work. So the converse proof shows that still we have infinitely long tails in the energy levels. This kind of new continuity will save the
Okay, cool. Thank you.
same statement. Yeah.
Hi, thanks for a nice talk. So I guess like you consider as a the entanglement bits that you start from, like you choose the finite dimensional thing that is embedded in this infinite dimensional system. Another like natural like entanglement standard might be like a two-mode squeeze state, like that's inherently continuous variable. Can your results be translated into some parameter like two-mode squeeze state that is needed to prepare some state row?
Between pure states, basically you can to begin, if you have a two-mode squeeze state, you can convert it into E bits. So between pure state, it's reversible basically. So basically, yeah, you could start with two-mode squeeze state, but
All right. So
yeah, we just follow the
in some
convention.
sense it's equivalent because it's
In my opinion, yeah.
Okay.
Yeah.
Thanks.
Like before this, it was not possible to find the entanglement of formation of like a two-mode squeeze state before your paper.
Entanglement of formation is it's defined in the previous paper. Yeah.
Okay.
Yeah, it's defined. Yeah, we give the we show the bound is our contribution.
Okay. So then I'm a little confused. What was the contribution?
Showing this bound. So we started with a number of bits. So this kind of bound. So entanglement formation, this value. So this is just a axiomatic function.
Okay.
So as an axiomatic function, it is defined. It has been defined. But how we show the same thing? Like how we show how to use this as for the characterization. This is our contribution.
Okay. Okay. Thank you.
If there are no more questions, let's thank the speaker again.
Thank you very much.